Okay, so today we're going to continue our discussion on convergence or divergence of infinite series. We're going to learn some new tests to figure out if a series converges or diverges. I would suggest if you have not watched the previous video that talked about the integral test and the test for divergence in P series, that you go back and watch that video first because we will reference things from that video. Okay, so today the tests that we are going to be talking about are comparison tests, ratio tests, and root tests. And before I even state any of these tests, remember that these particular tests that we're learning in the last couple of videos, they are not telling us exactly what a series converges to. They are just used to tell whether an infinite series converges or diverges, but we tend to not have any information about what the series actually converges to. All right, so we're going to start with the comparison test. The statement of the comparison test says, let's suppose that we have two series, AN and BN. So we have series with positive terms. Then here's a couple of true statements. If the series BN is convergent and if AN is less than or equal to BN for all N, then the series AN also converges. This is actually a pretty logical statement if you think about it. Remember what it means to be a convergent series. A convergent series is an infinite sum of terms, and it converges if once we add up all those infinite number of terms, we get a finite number. So what this is saying here is when I add up all the infinitely many terms of Bn, I get something finite. And all of the infinite terms of my AN happen to be smaller than all the infinite terms of my BN. So I'm adding up infinitely many terms still, but they're all smaller than what I had before. So if this one ended up being finite, well then the smaller one should be finite too. Makes sense. Works the other way as well. So our second part of the statement of the comparison test says that if Bn is divergent and our AN is greater than or equal to Bn for all N, then the series AN also diverges. And again, this is logical. This is saying if you add up all the infinitely many terms of Bn and get something infinite, well then if I add up even bigger things, it's still going to be infinite. Makes sense, doesn't it? Seems pretty simple. However, the comparison test, honestly, is what test that students struggle with quite a bit. The idea of the comparison test is not bad. The bad part is they don't give you the series that you're comparing to. A lot of times you yourself have to come up with a series that's appropriate to compare your given series to. And that's where the challenge comes in. So if you are going to use the comparison test, I personally highly recommend that you try to find either a geometric series or a P series to compare to, if at all possible. Why? Because we already know when geometric series converge or diverge, just like we know when a P series converges or diverges. So if you're having to come up with some series to compare stuff to, you might as well choose one that you know a lot about. So let's do an example of a comparison test. We are going to determine if this series the sum from 1 to infinity of 5 divided by 2n squared plus 4n plus 3, we're going to determine whether this converges or diverges. And like I said, we're going to use a comparison test here. So when I look at this series over here, 5 over 2n squared plus 4n plus 3, and remember that I'm plugging in larger and larger values of n all the way up to infinity. I know that as my n gets much, much bigger, this denominator here is dominated by this 2n squared. What I mean by that is when you plug in really, really big numbers, this 2n squared controls what's happening down here. The 4n and the plus 3 are so small in comparison to squaring that they don't really matter anymore. So what I'm going to do is I'm going to compare this series to a very similar series. I'm going to compare it to just 5 over 2n squared. It looks about the same as what we had before. I'm just cutting off part of the denominator. So I know that my original series, we know that the terms of the original series, so 5 over 2n squared plus 4n plus 3, this is always going to be something smaller than the terms of my new series, 5 over 2n squared. Why is that? Well, I'm plugging in positive numbers for my n, which means this denominator is larger than this denominator over here. When you divide by a bigger number, you get a smaller result. So this whole fraction is smaller than this whole fraction. So I'm hoping that I can show that this guy over here that I'm comparing to ends up being a convergent series, because then by my comparison test, the smaller guy will also be a convergent series. So let's take a look at this guy that I'm comparing to. The sum from 1 to infinity of 5 over 2n squared. What kind of series is this? Well, it just so happens to be a p-series, which we learned about in the last video. So I can take the series that I'm comparing to, 5 over 2n squared, and I'm going to rewrite it just slightly. I'm going to write this as 5 over 2 times the series from 1 to infinity of 1 over n squared, because now it looks just like our p-series. This is a p-series where my p happens to be equal to 2. Remember, the p in your p-series is referring to the power. Now all we have to do is remember what we learned in the last video. Does the p-series converge or diverge if we have numbers like 2? Well, remember that p-series converges if you have a p larger than 1. So since my 2 is bigger than 1, I know that that series converges. And now what does this mean? It means that the series I chose to compare to converges, but each term in that series was larger than the series I was given. So by my comparison test, the original series has to also converge. By comparison, our original series, which was 5 over a 2n squared plus a 4n plus 3, also converges. Now, do I have any idea what this thing converges to? No, no clue. But that's okay. They didn't ask us to find what it converges to. They only said, does it converge or diverge? And we answered the question that we needed to answer. So we are finished with that problem. Now, one thing that's a little strange about some of these tests is they are stated in very particular terms, but they actually work for some slightly less specific terms. Like, for example, this comparison test that we just learned, It's stating that your AN has to be less than or equal to BN all the time, or AN has to be greater than or equal to BN all the time, and that's not true. It just has to, at some point, satisfy those conditions. So I'm going to do another example of this comparison test where it doesn't satisfy the conditions of the comparison test all the time. It just satisfies the conditions eventually. And that's good enough to be able to use it. So our next example, does this series sum k equals 1 to infinity of the natural log of k over k converge or diverge? Now, those of you that just watched the video that came before this one about all of our integral tests and everything, right now you're wondering, well, hey, Dr. Katie, we did this one yesterday. And you're right. We did this exact same series in the previous video, but in the previous video, we figured out if this converged or diverged by using an integral test. And we found that it diverged in that video. Well, I'm going to do the same exact problem using a different test. We're going to use a comparison test. We already know this should diverge from the previous video, so it should still diverge today as well. So using a comparison test, since I happen to know that the natural log of k is bigger than 1 when k is bigger than e, and I mean, this is true, of course, but we're really only using integers in this problem. So I'm going to say that the natural log of k is bigger than 1 when k is larger than 3. Since I'm using integers, that's still a true statement there. Then I know that my natural log of k divided by k is going to be larger than 1 over k for k bigger than 3. Why is this true? Well, if I ignore the denominators right now, I have my natural log is larger than 1 when my k is bigger than 3. We already talked about that. And the denominators are the same on both of these, so that does not affect the inequality in any way. So what am I doing here? Giving us an idea of what to compare to. I'm going to compare this natural log of k over k series to the series 1 over k. So let's compare to the sum from k equals 1 to infinity of 1 over k. That is a very special series right there. You guys know what it is? Yeah, that's the harmonic series that we just talked about. And our harmonic series diverges. So my harmonic series diverges, and I'm saying that all of the terms of my harmonic series are smaller than all the terms in the series that I'm talking about. If the smaller guy diverges, so does the bigger one. So by the comparison test, my natural log of k over k also diverges. Not so bad. Again, the hard thing about the comparison test is figuring out what to compare to. And unfortunately, there's really no good way to tell you how to do that. You just have to build up an instinct, try your best to find a very similar looking series, but a familiar series. Things that are geometric, things that are P series, harmonic series, all of those are good options to try to compare to because we know when they converge or when they diverge. All right, so that's just the basic comparison test. We still have one more comparison test to learn before we move on to the ratio and the root test. So our next test is called the limit comparison test. The statement of the limit comparison test says that we should suppose that we have two series, AN and BN. These are series with positive terms, just like what we had before. Then this limit comparison test states that if the limit as n goes to infinity of the ratio AN over BN is equal to C, some finite number, and the C is also larger than 0, then either both series converge or both diverge. All right, that's kind of a strange statement, but that tells you something very important before we even try to use this test. This test doesn't tell you convergence or divergence directly. It just tells you that if you take these two series and take a limit of the ratio of the terms, and you get a number that's finite but positive, then they're either both convergent or both divergent. This is very important. That means that if you're trying to use this test, you need to make sure you're comparing your series to one that you actually know whether it converges or diverges. If you don't know if the one that you're comparing to converges or diverges, you're going to get stuck right after taking the limit. So you want to try to compare to things that you know already. P-series, geometric series, harmonic series, things along those terms. Let's do an example of this limit comparison test. We're going to test this series, 1 over 2 to the n minus 1 for convergence or divergence. And we are going to use that limit comparison test. So for the limit comparison test, it still helps to compare to a series that is close to what you're working with. I personally would try to ignore this minus 1 here and just look at 1 over 2 to the n. Let's compare to 1 over 2 to the n. And let's start by just taking the limit of the ratio of the terms and see what we get. My limit, as I approach infinity, of terms of my series that they gave me over the terms of the series that I'm comparing to, well, that looks pretty crazy. Let's go ahead and flip that bottom fraction and multiply by the reciprocal so that I get a limit of 2 to the n over 2 to the n minus 1. And now let's see what happens when I try to figure out this limit here. So what I would do in this particular problem, if you try to plug in infinity right now, we're at infinity over infinity. We don't know what that is. It could be infinite, could be 0, could be 1, could be anything. We have no idea what that is. So I would suggest that rather than jump into L'Hopital's rule, like a lot of people probably want to, I'm going to divide every single term in my problem by 2 to the n. So if I divide the top by 2 to the n, I get 1. And when I divide each term in the bottom by 2 to the n, I get a 1 minus 1 over 2 to the n. Why in the world did I do this? Well, because now when I try to take the limit, As n goes to infinity, this little guy here, 1 over 2 to the n, the denominator goes to infinity. So that means that this fraction is going to 0. That means my entire limit is going to 1 over 1 minus 0, which is 1. And now I got a finite number. And I got a finite number which is positive. So this means that my limit comparison test says that both series converge, or they both diverge, and I have to figure out which one this is. And see, this is what I was saying at the beginning. Make sure you're comparing to a series with some thought put into it. You want to make sure you know whether it converges or diverges. So let's take a look at the series we compared to. We compared to 1 over 2 to the n. This is a geometric series. I personally would write it as a 1/2 times a 1/2 to the n minus 1. Take a look at that, make sure you agree with that statement, but then notice that yes, this is in the proper form for our geometric series. This is a geometric series where the a happens to be 1/2 and my r happens to be 1/2 as well. We know the geometric series with absolute value of r, which in our problem is absolute value of 1/2 is less than 1, converges. So the series I compared to converges, which means the series that I was given, 1 over 2 to the n minus 1, also converges. All right, that's not too terrible. Though I will fully admit to all of you, I tend to not really use the comparison test or the limit comparison test. Sometimes it is the best choice, and you just have to build up that instinct for it, but they're personally not my favorite tests for figuring out convergence or divergence. My personal favorite is actually the next one we're going to do, the ratio test. I tend to go to ratio test all the time, but that doesn't mean it works all the time. Sometimes it still doesn't. So you need to know all of the tests so that if your favorite test happens to not work, you still have other options to use. All right, so let's talk all about our next test, the ratio test. The ratio test says to let an be a series with positive terms. And suppose that the limit as n goes to infinity of an plus 1 over an is equal to some number L. Then we have some true statements here. First true statement, if that L happens to be less than 1, series is going to converge. Then if L is greater than 1, the series diverges. And then the one downfall to this ratio test, if you get that that limit is exactly equal to 1, then this ratio test is inconclusive. We don't know anything. So that's one of the worst things that can happen when you're using a ratio test. If you do this limit and you get 1. And all that tells you is that, well, throw that out, pick another test, and try something different, because ratio test is not going to get you anywhere. But I found that a lot of the time it works pretty well, especially for problems that have powers and factorials in particular. So I'm going to do 2 examples using the ratio test. Does this series, sum from 1 to infinity of n over 2 to the n, converge or diverge? And again, I said we're going to use the ratio test on this one. That doesn't mean that you have to use the ratio test. It just means that that's the way I'm going to do it for this particular problem today. So for my ratio test, I have to I have to calculate the limit as n goes to infinity of my an plus 1 over an. Well, what does that mean? An plus 1 is what I get when I plug an n plus 1 in for all of my n's. So I'm going to get n plus 1 over 2 to the n plus 1. That's an plus 1. Then this needs to be divided by an, which is n over 2 to the n. Now, we already know that when we have a fraction divided by a fraction, I can flip the bottom, multiply by the reciprocal. I'm going to go ahead and do that rather than making it look terrible as a fraction over a fraction. So I'm going to multiply by this guy flipped upside down. 2 to the n over n. And now I'm going to try to calculate this limit. So this ratio test comes in handy when there's things that can cancel out. And on this problem, I notice that I have a 2 to the n up here, 2 to the n plus 1 down here. I'm going to have some cancellation. That 2 to the n is going to cancel out with all of these 2's except for one of them. So I get a limit as n goes to infinity, n plus 1 left on the top, a 2, and an n left on the bottom. And now this limit is one I can do pretty simply. I have the degree is the same on both of these, so the limit should be the ratio of the coefficients. I get 1/2. And now with this ratio test, we just have to check, did I get 1? Did I get something less than 1? Did I get something greater than 1? And we got something less than 1. The only hard part from here is remembering what that means. With ratio tests, if you get something less than 1 when you do the limit, that means that your series converges. And that's all there is to it. So this particular example wasn't too bad, but I need to do one that has some factorials in it and things. Ratio test works really well with factorials, but I find that students sometimes have issues canceling their factorials. So I want to do one where I show how that cancellation actually works. So let's try another example. And I'm going to be a little bit lazy and not erase my whole example up there because the instructions are going to be the same. So does this series, I'm going to start at k equals 3 to infinity, 2k factorial over 4 to the k. Does this series converge or diverge? And I'm going to use that ratio test again. So remember, your ratio test says that you need to do a limit to infinity, ak plus 1 over ak. So again, since I have a fraction in this problem, I'm going to already write it as my ak plus 1 times the reciprocal of ak, just to make it a little bit nicer to look at. So I get limit as k goes to infinity. Ak plus 1 is what I get when I plug a k plus 1 in for all my k's. Be very, very careful doing this. So before I even write the ak, take a look at how I wrote this. I had a 2k factorial, and I'm replacing the k with a k plus 1. That means I have 2 times k plus 1 in parentheses. Be very careful not to write it as 2k plus 1 without the parentheses. That's something totally different. So you have to think of replacing the k with a k plus 1. All right, so now I'm going to multiply by my a to the k, but flipped upside down. Okay, Okay, well, those factorials look a little bit scary. We'll make them look a little better in the next step. But the first thing I'm going to notice is I have cancellation here with my powers of 4. I have 4 to the k on top, 4 to the k plus 1 on the bottom. We get cancellation, leaving 1 4 in the denominator. So I have a 4 in the denominator. I have my 2k factorial. And I'm going to rewrite this guy a little bit by distributing. So I'm going to distribute that 2 and have a 2k plus 2 factorial. And believe it or not, we are going to have some cancellation here. We just have to remember what factorial means. Remember that when you have a factorial, you multiply the term that you have by the term 1 smaller and 1 smaller until you reach 1. So let me write out what this means using the definition of a factorial. I have a limit as k goes to infinity. 2k plus 2 factorial. That's 2k plus 2, 2k plus 1, 2k, 2k minus 1, and you keep multiplying all the way down to 1. That looks crazy. Then on the bottom, I have my 4, and then I have my 2k factorial. Well, 2k factorial is 2k, 2k minus 1, and you keep subtracting 1, multiply all the way down to 1. And now when it's written like this, you can see the cancellation much better. I get a lot of cancellation. In fact, this entire 2k factorial cancels out with this 2k all the way through the 1 on the top. All I have left in the numerator, 2k plus 2 and 2k plus 1. So I have a limit, k goes to infinity, 2k plus 2, 2k plus 1, all divided by 4. And now when I think about my k getting bigger and bigger and bigger, I'm getting something infinite on the top divided by 4. We're still infinite. Now, the important thing here is I got infinity, which is incredibly bigger than 1. So this means that my ratio test says this series divergence. All right, so that again, ratio test comes in handy when you have things that can cancel out very nicely. If you see a lot of factorials and powers and things, ratio test tends to work pretty good. All right, so all we have left for the video for today is one more test called the root test. So I'm going to give us the root test, and then we're going to do 2 examples of it, and that will be it for our material for today. Here's our statement of the root test. We're going to let AN be a series with positive terms. And we're going to suppose that the limit as n goes to infinity of the nth root of AN is equal to some number L. Then I have a bunch of true statements, kind of like I had for the ratio test. First, if that L happens to be less than 1, the series converges. Second, if my L is greater than 1, the series diverges. And just like our ratio test, there is one downfall to this test. If you get that limit equals 1, this particular test is inconclusive. And you would have to try a different test to determine if the series converged or diverged. So this root test, as you can imagine, works well if you have terms that are all to the same power. Because when you take the nth root of an nth power, you can think of those as canceling each other out, and then you get a nice limit to work with. So let's do an example of this guy. Does this series, the sum from k equals 2 to infinity of 4k minus 5 over 2k plus 1 to the kth power, converge or diverge? All right, so let's take a look at this problem first, because again, one of the hardest things about convergence tests is deciding what test to use. I'm going to use the root test because that's what I just taught you, but I would probably use the root test on this one anyway. Why? Because if I look at my series, I have all of my terms are to the same power, k. If I take a kth root of my terms, that root and that k will cancel each other out, and I just have to do the limit of what's left on the inside, and it shouldn't be too bad. So let's take a look. The limit as k goes to infinity of the kth root of the terms of my series. So I have the kth root of 4k minus 5 over 2k plus 1 to the kth power. And see, this is just what I was saying. That root and that power, they're now gone. This is exactly equal to the limit as k goes to infinity of 4k minus 5 over 2k plus 1. And this is a situation that we're pretty used to dealing with. The degrees are the same, numerator and denominator, so I get the ratio of the coefficients 4 over 2, which is 2, and the important thing is bigger than 1. All we have to remember then is what does greater than 1 mean for the root test? Means that the series diverges. All right, so again, when you have a power in your terms like this, everything to the same power, root test might be the way to go because the limit ends up being not too bad to calculate. I'm going to do one more example of this before we finish up this video for today. And it's going to be another one where we use this root test just to get some good practice in. So, does the series from 1 to infinity of 1 over the natural log of k plus 1 to the k power converge or diverge? All right, so some of you might even be wondering at this point, well, you were just saying that when the entire thing is to a power, the root test is a good idea. This doesn't have the whole thing to the k power, it just has the denominator to the k power. So why are you going to do the root test? Well, the reason is because the whole thing is to the k power. A 1 to the k would just be 1. So first thing I'm going to do is rewrite my series. And notice that this is the exact same thing. 1 over natural log of k plus 1, all to the k power. That's the exact same series that I have up there, it's just this one was simplified a little bit. So now if I use my root test, I would have to look at the limit as k goes to infinity of the kth root of these guys. I need a little more room to write under that root. So I have a kth root of 1 over natural log of k plus 1, all to the k power. the kth root, the kth power. Again, they cancel each other out. So we just have a limit as k goes to infinity of 1 over the natural log of k plus 1. And now I have to think about what happens to this natural log as the arguments get larger and larger. Well, as k goes to infinity, this natural log also goes to infinity. So my entire fraction is 1 divided by a really, really, really huge number, and that's going to go to 0. The important thing is that 0 is less than 1, so by my root test, the series converges. All right, so I know that was a lot of information. Learning all of the different tests for series convergence is quite difficult. So far, we know all about our test for divergence, an integral test, comparison test, limit comparison test, ratio test, root test. We already have 6 tests there. On top of knowing the actual definition of series convergence, of looking at the limit of the partial sums. The hardest thing about these sections is picking the test to use. Does it really matter? Not always. A lot of times different tests can be used and you still get the right result. However, sometimes one test is way harder than another test. My personal advice to you is pick a test that you like. Try to use that test as much as you possibly can. Don't forget the other ones because you might need them. But if you find one that you really truly like, try to use it every single time you can. And believe me, if the test is not going to work out so well, you'll know it pretty quick. The work will get very complicated. If it gets too complicated, there's no shame in throwing that out and trying a different test and starting over again. That's how you build your instinct. So that's all I have for you today. Make sure if you have any questions, leave them below. I'll get back to you as quick as I can. If you're in my classes currently, you are also welcome to ask me these questions in office hours or email, all of that. And I will see you guys the next time that we meet.